Welcome to Learn Chemistry Together. In this video, we are going to explore the fundamental concepts of induction and polar covalent bond. These principles dictate how molecules interact, how bonds are polarized, and how chemical reactivity unfolds. To understand bond polarity, we first look at electronegativity, an atom's inherent ability to attract shared electrons. This top reference table illustrates the periodic trends of electronegativity. Notice how values increase as you move from left to right across a row and from bottom to top up a column, with fluorine standing out as the most electronegative element at 4.0. When atoms with different electronegativities form a covalent bond, the electrons are shared unequally. The more electronegative atom pulls the electron cloud closer, acquiring a partial negative charge, while the less electronegative atom is left with a partial positive charge, creating a permanent dipole moment. How electronegativity differences drive molecular polarity and shape polar covalent bonds, using the visual framework provided in our diagram. 1. Electronegativity difference drives polarity. Hydrogen and fluorine example. In our top section, we examine hydrogen with an electronegativity value of 2.20 and fluorine with a much higher electronegativity value of 3.98. The electronegativity gap. Subtracting these values gives a large electronegativity difference, delta yen, of 1.78. 2. Unequal sharing, the polar covalent bond. When these atoms interact, this significant difference in pulling power dictates how the electron pair is shared. Unequal distribution. As shown in the lower section, a polar covalent bond results when atoms with different electronegativities share electrons unequally. Partial charges and dipoles. Because fluorine holds onto the electron density more tightly, it develops a partial negative charge, delta minus, while hydrogen is left with a partial positive charge, delta plus. This separation of charge creates a dipole moment, which is represented by a crossed arrow pointing toward the more electronegative atom. Magnified view. The magnified inset clearly illustrates how the electron cloud is heavily skewed toward the fluorine atom, emphasizing the lack of equal sharing. On the right-hand side of the diagram be the relative classification scale. We can categorize chemical bonds based on their delta yen ranges. Delta yen less than 0.4 represents nonpolar covalent bonds, where electrons are shared relatively equally, for example, HH. Delta yen between 0.5 and 1.9 represents polar covalent bonds, which fall right into our primary discussion zone, for example, HF. Delta yen greater than 2.0 represents ionic bonds, where the difference is so extreme that electron transfer dominates over sharing, for example, NaCl. Building on bond polarity, the inductive effect describes the polarization of a sigma bond caused by a neighboring electronegative atom or functional group. Unlike temporary electrostatic fields, this is an inherent, permanent redistribution of electron density along the backbone of a molecule. Electron withdrawing groups. EWG on the left side. Electron withdrawing groups involve atoms or substituents that are more electronegative than carbon. The effect: they pull electron density away from neighboring atoms, creating what is known as the negative inductive I effect. Examples. Common examples include halogens like fluorine, F, and chlorine, Cl, nitro groups, and O2, hydroxyl groups, OH, and alkoxy groups, or. Electron donating groups. EDG on the right side. Electron donating groups are typically less electronegative or electron releasing. The effect: they push electron density toward neighboring atoms, resulting in the positive inductive plus I effect. Examples. Common examples include alkyl groups like methyl CH3, ethyl CH2CH3, and carboxylate anion COO. Key characteristics of inductive effect. Permanent polarization. The shift in electron density is a permanent feature mediated entirely through single sigma bonds. Distance dependent. The influence of the inductive effect drops off rapidly, decreasing significantly with distance as you move further away from the electronegative source or substituent. These electronic effects have profound practical consequences in chemistry. Polar bonds create specific sites of high and low electron density that dictate susceptibility to nucleophilic or electrophilic attack. Furthermore, inductive effects heavily influence acidity. Here is the detailed discussion of chemical consequences, reactivity, acidity, and basicity. 1. Reactivity, polar bonds and attack. Sites of high and low electron density. Polar bonds create localized regions of partial positive, delta plus, and partial negative, delta, charge within a molecule. Nucleophilic attack. Electron-rich species, known as nucleophiles, new smiley face, target electron-deficient centers, such as the carbon atom bonded to a halogen like bromine in our example, leading to nucleophilic attack and substitution or addition products. Electrophilic attack. Conversely, electron-poor species or regions can be targeted by electron-rich centers, resulting in electrophilic pathways and distinct attack products. 2. Acidity and basicity. Inductive effects. Influence on acidity. Inductive effects strongly influence the acidity of organic molecules by stabilizing or destabilizing conjugate bases through electron withdrawal. Carboxylate anion stabilization. As shown in our comparison of acetic acid derivatives, substituting the methyl group with increasingly electronegative groups from CH3 to Cl to CF3 enhances electron withdrawal. pK trends and acid strength. Acetic acid has a pK to approximate 4.76. Chloroacetic acid features a chlorine substituent, lowering the pK to approximate 2.87. Trifluoroacetic acid features 3 highly electronegative fluorines on the trifluoromethyl group, dramatically lowering the pK to approximate 0.23. In conclusion, increasing the electronegativity of the substituent leads to increased electron withdrawal, greater stabilization of the carboxylate anion, higher acid strength, and correspondingly lower pK values. Thank you for watching and click subscribe for more.